end-to-end development platform for out-of-order RISC-V multi-core processors. In modern process design, execution strategy is key to performance. Traditional in-order processors execute instructions sequentially, often stalling on data or control dependencies. Out-of-order execution enhances efficiency by reordering instructions dynamically, maximizing resource utilization and boosting throughput for complex workloads. Our journey builds upon the foundation laid by Batch 18, who developed a RISC-V in-order core and out-of-order core, paving the way for our work on a multi-core system that pushes performance further through parallelism. Single-core processors struggle with complex workloads, creating performance bottlenecks. Multi-core processors overcome this by running tasks in parallel, enabling faster, more efficient computing across modern systems. Although we need to increase the number of cores, we can't simply connect them and expect it to work correctly, as in reality, each core operates on its own cache copy of the shared data. When one core updates its cache, other cores may still hold and operate on outdated version of that data, leading to inconsistencies. This can result in the program producing incorrect or unexpected results, which is known as coherency problem. This can be solved with the proper implementation of coherency protocol in the interconnect. Our project motivation is to create an accessible learning platform for developing multi-core processors. Existing open source multi-core frameworks are too complex for beginners, so we built a modular, FPGA synthesizable multi-core RISC-V processor designed to empower students and researchers without overwhelming them. Our project delivers three key components: a multi-core emulator, a fully functional chisel-based out-of-order processor available in single, dual, and quad-core versions, and a complete verification environment for hardware research and parallel programming. We develop a RISC-V emulator that supports multi-core configurations and is tailored for debugging and verification. It includes a core local interrupter for inter-core communication, timer support, and software interrupts. We have successfully booted multi-core no MMU Linux images, run multi-threaded applications, and validated features like synchronization and shared memory. This emulator provides a reliable platform for testing architectural features and software early without needing physical hardware. This is the high-level block diagram of our quad-core processor, showcasing the key architectural components and how they work together. Our design built on an out-of-order core originally developed by FIP18 group. Since the core was designed with a composable architecture, we were able to integrate new modules seamlessly to create a functional multi-core processor. We began by redesigning the instruction fetch unit and integrated an advanced stage branch predictor to reduce the branch misprediction penalty and improve the pipeline efficiency. We also reworked the memory access unit and data cache. The new data cache is non-blocking, supports cache coherence, uses a pseudo LRU replacement policy, and includes misstatus handling registers for handling multiple outstanding memory accesses. To support multi-core communication, we develop a cache-coherent interconnect that links all cores to a shared lower-level cache. It follows a snooping-based protocol and implements the MoASI cache-coherent protocol using the industry-standard AXIACE interface. This ensures consistency across cores during shared memory operations. Finally, we implemented a 2 MB level 2 shared cache. It's non-blocking, uses the PLRU policy, and supports multiple concurrent memory transactions with the help of MSHRs and reorder buffer. Together, these components form a robust, high-performance multi-core processor architecture suitable for parallel workloads. Our development workflow includes both software and hardware verification paths. On the software side, we write multi-threaded C programs for bare metal RISC-V, compile them with a cross-compiler, and use our emulator for early debugging, allowing us to verify logical correctness without deploying to hardware. For hardware development, we use Chisel to describe our multi-core architecture, which is compiled into synthesizable Verilog. We then simulate using cycle-accurate core simulation with a log-step run, which synchronizes the software and hardware models for precise debugging. Waveform dumps and tools like header file generation and platform API further aid in tracing and integration. Finally, we deploy the design to FPGA using the Vivado flow. At runtime, a serial terminal and USB interface allow user interaction, while the integrated logic analyzer helps capture on-chip signal transitions enabling real-time debugging and in-depth validation of our hardware. Our performance results demonstrate varying level of speed up across different workloads. These workloads are based on standard RISC-V benchmarks modified to evaluate multi-core processors by incorporating multiple data sizes. As shown in the diagram, there is a clear and noticeable performance improvement when using dual-core and quad-core processors compared to single-core processor, particularly during the execution of parallelizable algorithms. Additionally, performance continues to improve as data sizes increase, highlighting the growing importance of multi-core processor in today's computing landscape. We invite you to use this platform to explore parallel architecture firsthand and take your first step toward building tomorrow's high-performance systems.